So in section 3.2, we're going to talk about the derivative of the exponential function. So we're not going to try to prove it, but kind of just looking at it a little bit, if there's a graph of y equals a to the x, there's some things that we can notice about this. The original function, if we're calling this our f of x equals a to the x, then we know that f is always positive. We can see that it's increasing from left to right for the whole domain. So that means f prime must also always be positive. Kind of interesting there. And if we think a little bit, I don't know if you've thought about this, but we use an exponential, y equals a to the x, is also often used as a population model. You know, that it models population growth. And one of the reasons for that is because we say the rate of change of a population is proportional to the population. That is, the rate of change, which we would call the derivative of that population, is proportional to the population that we had right there, that its derivative is proportional to that. And so that, in fact, is true. So I'm not really trying to prove that. But what we see is that the derivative of some a to the x power, any exponential, is going to be that same exponential times some constant k. And it turns out that k is the natural log of the base. So what we're saying then is, for example, the derivative of 5 to the x is going to be that same exponential 5 to the x times the derivative of its base, natural log 5. It also means that, say, 3 to the x, its derivative, so let me say if it's f of x, then we would say that f prime of x is going to be 3 to the x times natural log of 3. It means that if we say y is equal to 7 to the x, then dy dx, using Leibniz notation, is 7 to the x times the natural log of 7. But here's the kicker. Here's the part that makes us like Euler's number e so much. Its derivative is going to be that same e to the x times the natural log of the base. But the natural log of e is 1. This is huge. This is our new favorite derivative. The derivative of e to the x is just itself e to the x. How great is that? Pretty great. So we can do some weird things. Let's see what we've got. If we say f of x, using what we already know, is equal to, say, 4x to the 5th plus, let's say, 7e to the x plus maybe 3 times 4 to the x plus maybe pi raised to the e power. And if we want to find its derivative using what we know before, here is our power rule. The 5 comes down, multiplies the 4, becomes 20. We subtract 1 from the exponent, it's x to the 4th. Now we get to use a constant times a function. Is the derivative is the same constant, just hangs out. And the derivative of e to the x we love, it's e to the x. And 4 to the x we don't love so much. It's going to be times 4 to the x, and then you have to take it times that natural log of its base 4. And if we have pi to the e, before we get too worked up, we see that that's really just a constant, and so its derivative is going to be 0. So some interesting things. If we have something like f of x is equal to, say, a to the 5x power, we can think of this also as being a to the 5th raised to the x. So now this is really just, say, b to the x. So its derivative is going to be the same base b to the x times the natural log of that base. So in our case, we're going to get that same a to the fifth to the x times the natural log of its base, a to the fifth. But with a little cleanup, we can see that a to the fifth to the x, that's just our same a to the 5x that we had before. We can use properties of logarithms and bring that 5 out in front, but I'm going to bring it all the way out in front to the 5a to the 5x times the natural log of a. So somehow we see something happening. There's something bigger happening right here between those 5's, but we'll talk about that more in a little bit. It's kind of interesting to see right now anyway. So I'm going to go to a new panel here, and I want to do another kind of problem here. Let's find an equation of a tangent line again, which we have done often. Equation of a tangent line to, we're going to say f of x equals e to the x, and we'll say at x equals e squared. And then we're also going to find what's called the equation of the normal line. So find an equation of the normal line, also to f, also at x equals e squared. So first, the tangent line. We need to know that what its derivative is. So f prime of x is just e to the x. It's its own derivative. And so f prime evaluated at e squared is going to be, here's a weird looking number, e to the second. That's going to be our slope. And our point, when we plug in f of e squared, we get this weird e to the second. So our tangent line is going to be y minus our y coordinate, which was at e to the second, is equal to our slope, e to the second, times x minus e to the second. Well, granted, that was pretty weird. A normal line, now what a normal line is perpendicular to the tangent line at the point of tangency. So it's perpendicular to the tangent line. So if we know our slope is from the tangent line is e to the second, then the slope of the line perpendicular to that is going to be negative 1 over e to the second. It's the negative reciprocal. So our normal line is going to be at that same point, 1 minus e to the second equals the slope, which in the case of the normal is going to be 1 over e to the second times x minus that. So anyway, that's our normal line. So that's, now there's some things we don't know yet. So just so for the record, things we don't know, but we will learn eventually. So we don't know right now how to find, say, the derivative of a function times a function. So we don't know how to take the derivative of x squared times e to the x. We don't know how to find the derivative of a quotient, say e to the x over x. We don't know how to do that yet. We don't know yet how to do this derivative of composite functions, like e to the x squared, okay, where we have something more complicated than just x in our exponent. And we don't know how to do something really weird like x to the x, where we have a function raised to a function power. But all these are coming in the days ahead. We don't have to wait very much longer.